Welcome back, and in this lesson I want to cover a few really important topics which will be super useful as you progress your general IT career, but especially so for anyone who is working with traditional or hybrid networking. Now I want to start by covering what a VLAN is and why you need them, then talk a little bit about trunk connections, and finally cover a more advanced version of VLANs called Q-inQ. Now I've got a lot to cover, so let's just jump in and get started straight away. Let's start with what I've talked about in my technical fundamentals lesson so far. This is a physical network segment. It has a total of 8 devices, all connected to a single Layer 2 capable device, a switch. Each LAN, as I've talked about before, is a shared broadcast domain. Any frames which are addressed to all Fs will be broadcast on all ports of the switch and reach all devices. Now this might be fine with 8 devices, but it doesn't scale very well. Every additional device creates yet more broadcast traffic. Because we're using a switch, each port is a different collision domain, and so by using a switch rather than a Layer 1 hub, we do improve performance. Now this local network also has 3 distinct groups of users. We've got the game testers in orange, we've got sales in blue, and finance in green. Now ideally we want to separate the different groups of devices from one another. In larger businesses you might have a requirement for different segments of the network for normal devices, for servers, and for other infrastructure. Different segments for security systems and CCTV, and maybe different ones for IoT devices and IP telephony. Now if we only had access to physical networks, this would be a challenge. Let's have a look at why. Let's say that we took each of the 3 groups and split them into either different floors or even different buildings. On the left, finance, in the middle, game testers, and on the right, sales. Each of these buildings would then have its own switch, and the switches in those buildings would be connected to devices also in those buildings, which for now is all of the finance, all of the game tester, and all of the sales team's machines. Now these switches aren't connected, and because of that, each one is its own broadcast domain. This would be how things would look in the real world if we only had access to physical networking, and this is fine if different groups don't need to communicate with others, so if we don't require cross-domain communication. The issue right now is that none of these switches are connected, so the switches have no Layer 2 communications between them. If we wanted to do cross-building or cross-domain communications, then we could connect the switches, but this creates one larger broadcast domain, which moves us back to the architecture on the previous screen. What's perhaps more of a problem in this entirely physical networking world is what happens if a staff member changes role but not building. In this case, moving from sales to games tester. In this case, you need to physically run a new cable from the middle switch to the building on the right. If this happens often, it doesn't scale very well, and that is why some form of virtual local area networking is required, and that's why VLANs are invaluable. Let's have a look at how we support VLANs using Layer 2 of the OSI 7-layer model. This is a normal Ethernet frame. In the context of this lesson, what's important is that it has a source and destination MAC address fields together with a payload. Now the payload carries the data. The source MAC address is the MAC address of the device which is creating and sending the frame. The destination MAC address can contain a specific MAC address, which means that it's a unicast frame, so a frame that's destined for one other device, or it can contain all Fs, which is known as a broadcast, and it means that all other devices on the same Layer 2 network will see that frame. What a standard frame doesn't offer us is any way to isolate devices into different parts, different networks, and that's where a new standard comes in handy, which is known as 802.1q, also known as .1q. .1q changes the frame format of a standard Ethernet frame by adding a new field, a 32-bit field in the middle in cyan. The maximum size of the frame as a result can be larger to accommodate this new data. 12 bits of this 32-bit field can be used to store values from 0 through to 4095. This represents a total of 4096 values. This is used for the VLAN ID or VID. A 0 in this 12-bit value signifies no VLAN, and 1 is generally used to signify the management VLAN. The others can be used as desired by the local network admin. What this means is that any .1Q frames can be a member of over 4,000 VLANs, and this means that you can create separate virtual LANs or VLANs in the same Layer 2 physical network. A broadcast frame, so anything that's destined to all Fs, would only reach other devices which are in the same VLAN. Essentially, it creates over 4,000 different broadcast domains in the same physical network. You might have a VLAN for CCTV, a VLAN for servers, a VLAN for game testing, a VLAN for guests, and many more. Anything that you can think of and can architect can be supported from a networking perspective using VLANs. But I want you to imagine even bigger. Think about a scenario where you as a business have multiple sites and each site is in a different area of the country. Now each site has the same set of VLANs. You could connect them using a dedicated wide area network and carry all of those different company-specific VLANs, and that would be fine. But what if you wanted to use a comms provider, a service provider who could provide you with this wide area network capability? What if the comms provider also uses VLANs to distinguish between their different clients? Well, you might face a situation where you use VLAN 1337 and another client of the comms provider also uses VLAN 1337. Now, to help with this scenario, another standard comes to the rescue, 802.1ad, and this is known as Q-inQ, also known as provider bridging or stacked VLANs. This adds another space in the frame for another VLAN fields. So now instead of just the one field for 802.1q VLANs, now you have two. You keep the same customer VLAN field, and this is known as the C tag or customer tag, but you add another VLAN field called the service tag or the S tag. This means that the service provider can use VLANs to isolate their customer traffic while allowing each customer to also use VLANs internally. As the customer, you can tag frames with your VLANs, and then when those frames move onto the service provider network, they can tag with the VLAN ID which represents you as a customer. Once the frame reaches another of your sites over the service provider network, then the S tag is removed and the frame is passed back to you as a standard .1Q frame, with your customer VLAN still tagged. Q-inQ tends to be used for larger, more complex networks, and .1Q is used in smaller networks as well as cloud platforms such as AWS. For the remainder of this lesson, I'm going to focus on .1Q, though if you're taking an advanced networking course of mine, I will be returning to the Q-inQ topic in much more detail. For now though, let's move on and look visually at how .1Q works. This is a cut down version of the previous physical network I talked about, only this time, instead of the 3 groups of devices, we have 2. So on the left we have the finance building, and on the right we have game testers. Inside these networks we have switches, and connected to these switches are 2 groups of machines. These switches have been configured to use 802.1q, and ports have been configured in a very specific way, which I'm going to talk about now. Now what makes .1Q really cool is that I've shown these different device types as separate buildings, but they don't have to be. Different groupings of devices can operate on the same Layer 2 switch, and I'll show you how that works in a second. With 802.1q, ports in switches are defined as either access ports or trunk ports. An access port generally has one specific VLAN ID or VID associated with it. A trunk conceptually has all VLAN IDs associated with it. So let's say that we allocate the finance team devices to VLAN 20 and the game tester devices to be VLAN 10. We could easily pick any other numbers. Remember, we have over 4,000 to choose from, but for this example, let's keep it simple and keep 10 and 20. Now, right now, these buildings are separate broadcast domains because they have separate switches which are not connected, and they have devices within them. 2 laptops connected to switch number 1 for the finance team, and 2 laptops connected to switch number 2 for the game tester team. Now, I mentioned earlier that we have 2 types of switch ports in a VLAN-capable network. The first are access ports, and the ports which the orange laptops on the right are connected to are examples of access ports. Access ports communicate with devices using standard Ethernet, which means no VLAN tags are applied to the frames. So in this case, the laptop at the top right sends a frame to the switch, and let's say that this frame is a broadcast frame. When the frame exits an access port, it's tagged with the VLAN that the access port is assigned to, in this case VLAN 10, which is the orange VLAN. Now, because this is a broadcast frame, the switch now has to decide what to do with the frame, and the default behaviour for switches is to forward the broadcast out of all ports except the one that it was received on. For switches using VLANs, this is slightly different. First, it forwards to any other access ports on the same VLAN, but the tagging will be removed. This is important because devices connected to access ports won't always understand 802.1q, so they expect normal untagged frames. In addition, the switch will forward frames over any trunk ports. A trunk port in this context is a port between 2 switches, for example this one between switch 2 and switch 1. Now, a trunk port is a connection between 2 .1q capable devices. It forwards all frames and it includes the VLAN tagging. So in this case, the frame will also be forwarded over to switch 1 tagged as VLAN 10. Which is the game tester VLAN. So tagged .1q frames, they only get forwarded to other access ports with the same VLAN, but they have the tag stripped, or they get forwarded across trunk ports with the VLAN tagging intact. And this is how broadcast frames work. For unicast ones which go to a specific single MAC address, well, these will be either forwarded to an access port in the same VLAN that the specific device is on, or if the switch isn't aware of the MAC address of that device in the same VLAN, then it will do a broadcast. Now, let's say that we have a device on the finance VLAN connected to switch 2, and let's say that the bottom left laptop sends a broadcast frame on the finance VLAN. Can you see what happens to this frame now? Well, first, it will go to any other devices in the same VLAN using access ports, meaning the top left laptop. And in that case, the VLAN tag will be removed. It will also be forwarded out of any trunk ports tagged with VLAN 20, so the green finance VLAN. It will arrive at switch 2 with the VLAN tag still there, and then it will be forwarded to any access ports on the same VLAN, so VLAN 20 on that switch, but the VLAN tagging will be removed. Using virtual LANs in this way allows you to create multiple virtual LANs or VLANs. With this visual, you have 2 different networks. The finance network in green, so the 2 laptops on the left and the one that's middle bottom. And then you have the game testing network, so VLAN 10, meaning the orange one on the right. Both of these are isolated. Devices cannot communicate between VLANs, which are layer 2 networks, without a device operating between them, such as a layer 3 router. Both of these virtual networks operate over the top of the physical network, and it means that now we can configure this networking using virtual configuration, software which can be configured on the switches. Now, VLANs are how certain things within AWS, such as public and private VIFs on Direct Connect, work, so keep this lesson in mind when I'm talking about Direct Connect. A few summary points though that I do want to cover before I finish up with this lesson. First, VLANs allow you to create separate Layer 2 network segments, and these provide isolation, so traffic is isolated within these VLANs. If you don't configure and deploy a router between different VLANs, then frames cannot leave that VLAN boundary, so they're virtual networks, and these are ideal if you want to configure different virtual networks for different customers, or if you want to access different networks, for example when you're using Direct Connect to access VPCs. VLANs offer separate broadcast domains, and this is important. They create completely separate virtual network segments, so any broadcast frames within a VLAN won't leave that VLAN boundary. If you see any mention of 802.1q, then you know that that means VLANs. If you see any mention of VLAN stacking or provider bridging or 802.1ad or Q-inQ, this means nested VLANs, so having a customer tag and a service tag allowing you to have VLANs in VLANs, and these are really useful if you want to use VLANs on your internal business network and then use a service provider to provide wide area network connectivity who also uses VLANs. And if you are doing any networking exams, then you will need to understand Q-inQ as well as 802.1q. Now don't worry, if you're watching this video as part of my Advanced Networking Specialty course, I will be having a separate lesson which covers Q-inQ in much more detail because you will need a much wider knowledge of this feature for the exam. If you're not doing that certification, then this is all of the information that you'll need in order to be able to understand VLAN tagging as well as do basic or intermediate integration between traditional networks and AWS. So with that being said, that's everything I wanted to cover, so go ahead and complete this video, and when you're ready, I'll look forward to you joining me in the next.